Integrating a custom language or rule evaluator into a Win64 application typically creates a conflict between execution speed and architectural complexity. The easiest path is to embed an interpreted language or a bytecode interpreter, but you pay for that convenience with performance overhead, as the CPU has to translate instructions on the fly instead of executing them directly. The alternative is embedding a heavy, production-grade compiler toolchain, like LLVM. That brings significant architectural weight, complex C++ API bindings, and gigabytes of external dependencies. Enter Viper. Viper is a dynamic, native Win64 runtime environment built entirely within Delphi. By removing the need for external linkers, parsing engines, or third-party binaries, an application can compile and execute raw machine code internally. The entire Viper toolchain is contained within a single uses Viper clause in a Delphi project. There are no external DLLs or separate compiler installations required. It bypasses the traditional source parsing phase. There is no text to tokenize and no syntax tree to analyze. Instead, the first stage relies on a programmatic Delphi API. Developers define their logic by calling methods directly in code. This block flow diagram shows the resulting three-stage pipeline. The Delphi API generates what is called a static single assignment, or SSA, intermediate representation. SSA is a form of intermediate code where every variable is assigned exactly once, making it mathematically predictable for the next stage, the optimizer. From there, the optimized code passes to the machine code generator. The final stage splits into two distinct emission targets. Viper can compile ahead of time, meaning it writes a physical binary file to the disk, or just in time, where it compiles directly into the system's active RAM for immediate use. By keeping every step, from the intermediate representation to the final linking inside a single process, the system avoids the context-switching delays of calling out to an external compiler. Most compilers spend computational energy reading and interpreting text files. Viper drops this step entirely. The developer acts as the compiler's front-end. You build the program logic using explicit, typed expression handles within Delphi. Every variable has a strictly known size. The API requires you to declare fixed size types, like standard 8 to 64-bit integers, or IEEE 754 floating point types. There are no implicit conversions. You can programmatically define structured data, like records and unions. Viper calculates the exact caching and alignment so that these structures match the strict memory layout rules of the C Application Binary Interface, or ABI. This comparison shows method chaining constructing logic. Calling methods like let or add on the left instantly builds the node graph on the right. For rapid prototyping, developers can replace verbose names with single-letter aliases, like I for integer or V for variable. Translating logic directly into a strongly typed node graph eliminates the ambiguity of parsing text strings. The compiler never has to guess what a line of code means, saving both memory and processing time. The raw intermediate representation graph we just built is structurally complete, but it is not fast. It needs to be optimized before it becomes machine code. Viper includes a multi-pass optimizer. At optimization level 0, the debug state, the code is left unoptimized to ensure the logic runs exactly as written. However, level 0 automatically injects internal counters into the graph. These track every memory allocation on the heap, allowing the runtime to report any memory leaks the moment the program halts. Moving to optimization levels 1 and 2 strips away that debug and tracking overhead, preparing the code for pure performance. This diagram shows the optimizer in action. Constant folding and copy propagation resolve static values, merging them into single data points. Final passes employ common sub-expression elimination to remove repeated calculations and dead code elimination, deleting logic that doesn't affect the final output. Applying these mathematical transformations directly to the intermediate representation guarantees that the final native machine code will execute at maximum CPU efficiency, without the developer having to hand-tune their Delphi inputs. With the optimization complete, the code generator takes over. But raw x86-64 opcodes cannot simply exist in a vacuum. They require a structured execution environment to run on an operating system. The backend maps potential hardware faults, like dividing by 0 or accessing restricted memory, directly into Windows Structured Exception Handling, or SEH. SEH is the native Windows mechanism for catching hardware and software errors safely. For external interactions, Viper implements C++ Atanium name mangling by default. This encodes parameter types directly into the function symbol name, allowing for function overloading where multiple functions share the same name but take different arguments. Alternatively, developers can switch to standard C linkage. This strips away the name mangling entirely, creating clean, predictable exports for dynamic link libraries. This animation illustrates the ahead-of-time emission process. The raw x86-64 instructions are wrapped inside a portable executable and common object file format structure, universally known as PE/COF. This header contains the metadata Windows needs to load the file. If the code needs to call external Windows APIs, Viper writes those dependencies directly into the PE import table. The Windows loader then automatically resolves those system calls when the program starts. The code generator can output several physical file formats: standard executables, dynamic link libraries, or static library and object files for external linking. Because Viper natively implements standard OS features like SEH and strict ABI memory layouts, the output is a true system-level binary. It is not a sandbox script running inside an emulator. Emitting files to a hard drive isn't always fast enough for dynamic environments. The alternative is bypassing the file system entirely using just-in-time or JIT compilation. This grid represents system memory. When calling build JIT, Viper triggers virtual alloc, asking Windows for a specific block of RAM. Crucially, it requests the page execute read write flag. This permission allows Viper to write raw machine code into the block and immediately execute it. The host Delphi application interacts with this newly populated memory using Viper's tJIT interface, which maps function names to their precise hardware addresses in RAM. Execution occurs via the invoke method. The application passes parameters precisely as the OS expects, and raw machine code executes at full native CPU speed. If the JIT compiled function returns a floating point number, the host retrieves it by reading directly from the Win64 XMM0 hardware register, adhering strictly to the system's calling conventions. If the logic needs to change, developers can call reset build. This clears the compiled backend state but preserves the intermediate representation, allowing for instantaneous recompilation with new parameters. By eliminating hard drive input-output and linking everything directly in active memory, complex rule engines and scripting systems achieve zero overhead adaptability at runtime. This diagram shows the complete pipeline we've just covered, from the programmatic API, through the SSA optimizer, out to the hardware-level x86-64 emission targets, all encased in a single boundary. The entire process runs in pure Object Pascal. There are no external toolchains, no parsers to configure, and no complex C++ template metaprogramming to wrestle with. This architecture enables high-performance scenarios that require direct machine code execution, such as game modding systems, mathematical formula evaluators, or dynamic plugins. And developers can implement all of these features without ever leaving the Delphi ecosystem. If issues arise, built-in diagnostic tools like the SSA dump allow engineers to inspect the intermediate representation before compilation, exposing exactly how the optimizer transformed the logic. The final output, whether written to disk or compiled into active memory, is completely standalone. It requires no runtime installations or external dependencies. By collapsing the footprint of a traditional compiler into a single runtime library, host applications gain an elegant, uncompromising path to raw CPU execution.